Welcome guys to today's class. First of all, I want to say a very big thank you to you guys for watching my videos, for liking my videos, for commenting, and for sharing to your friends and classmates. Thank you, God bless. Today we want to discuss another important topic in chemistry. Yes, as you can see on the board, ionic and chemical equilibrium. Before we proceed, we want to recall to ourselves some important points we know about acid and base. Yes, one is strong acids. And the second is strong base. The next is weak acid. And the next is weak base. When you hear or when you come across the word weak, strong acid, when you come across the word strong acid, what comes to your mind? Answer. It simply means acids which has the tendency to what? Ionize completely in water. Acids which has the tendency to ionize completely in water. What are the examples? You talk about HCl, H2SO4, HNO3, etc. That means nitric acid, sulfuric acid, hydrochloric acid. That is what we mean. When we talk about strong base, it also means bases which have the tendency to ionize completely in water. Yes, example of strong base we have are sodium hydroxide, potassium hydroxide, etc. They have the tendency to ionize completely in what? Water. What do we mean by weak acids? Weak acids simply mean acids which have the tendency to ionize partially in water. Acids which have the tendency to ionize partially in water. There you come to see organic acids as examples, such as ethanoic acid, lactic acid, and so on. Let's see example, CH3COOH. This is what we call ethanoic acids. These ethanoic acids have the tendency to ionize partially in water. That means when you dissolve it in water, the implication is that it will have two things. It will have the unionized part and it will have the ionized part. That is what we are meant by calling an acid a weak acid. A weak acid simply means acid which has the tendency to ionize partially in water. That means it has the unionized part and it has the ionized part. Then for weak base, likewise, weak bases are bases which have the tendency to ionize partially in water. Yes, that means examples, you'll be talking about ammonium hydroxide. It's an example of weak base we have. That means this we have the unionized part and the what? Ionized part. That is the reason why we say it ionized partially. So it must have the unionized part and ionized part. What is the essence of discussing this ionic and chemical equilibrium? Most manufacturing companies or all the manufacturing companies take recognizance of this topic while doing their production. Yes. Take for instance, pharmaceutical industries. When a drug is to be what? Manufactured, one of the points we consider is to ensure that we do not produce this as a strong acidic drugs or strong basic drugs. Yes, Because when you produce it as a strong acidic drug or as a strong basic drug, the implication is that it will ionize completely. When taken into the body, it will ionize completely. And ionizing completely simply means that the body will not make use of it. Yes, the body will not make use of it. But when you produce a drug as weakly acidic or weakly basic drug, the implication is that it will have the unionized part, and this is what we are concerned with while doing our work manufacturing. Yes, while manufacturing any drug, any food, any canned food and all have you, we consider these points. Is it a weakly acidic or strongly acidic? We make sure that it is manufactured as what? Weakly acidic way or weakly basic way, so as when taken into the body, after digestion and everything must have taken place, it will get what? The unionized part. This unionized part is a part or the part of it that the body will make use of. That means it is the unionized part that will get absorbed either through the stomach or through the small intestine. If it is acidic drug, most acidic drugs are what? Absorbed through the stomach. Why? Because the acidic drugs are acidic in nature, weakly acidic. The weakly acidic drugs are weakly acidic, and the pH of the stomach is also what? Acidic. And so to avoid bringing up ionization or making it not to what? Be absorbed into the body, it is manufactured so as it will get absorbed through the stomach to the bloodstream. And when it is absorbed through the stomach, the implication is that the body will make use of it. But when weakly acidic drug goes to the small intestine, which most part of it are alkaline in nature or basic in nature, there will be neutralization. And when there is neutralization reaction, the outcome will be ionized and the drug will not be absorbed. It will be absorbed poorly or may not be absorbed at all. It will be absorbed poorly or may not be what? Absorbed at all. Yes, depending on the degree of ionization that occurs there. Now, so there is need for weakly acidic drugs to be produced instead of strong acidic drugs, so as to see that why after the absorption and digestion has taken place, it will produce what? Unionized part of it, which the body will make use of. And we said the weakly acidic is best absorbed through the what? Stomach, while the weakly basic is best absorbed to the bloodstream through the what? Small intestine. That is the part of GIT. Yes, it is part of the GIT. The GIT is made up of 3 partitions: the esophagus, the stomach, and the small intestine. So it's part of the GIT we have, or is a fraction of the GIT. And so the weak basic drugs is absorbed through the what? Small intestine, while the weak acidic drugs is absorbed through the what? Through the stomach. Okay, next for us to discuss is theories of acids and base. We have many theories on acid and base. We want to discuss 3 of such theories, and one of it is Arrhenius' concept of the theorem of acid and base. Arrhenius' concept of acid and base. And the second is Bronsted and Rowley theory. Bronsted and Rowley concept of the acid and base. And number 3 is the Lewis concept. So I want to discuss them one after the other. When we discuss Arrhenius' concept of acid and base, for the acid part, Arrhenius says that acids are substances which dissolves in water to produce what? Hydrogen ion. Acids are substances which dissolves in water to produce what? Hydrogen ion. Whereas bases are substances which dissolves in water to produce what? Hydroxyl ion. Bases are substances which dissolves in water to produce what? Hydroxyl ion. Yes, that means his own concept is limited to dependence in water. Yes, that means once you are to produce hydrogen ion or hydroxyl ion, you have to dissolve the acid in water. Yes, and so that is about Arrhenius' concept of acids and base. Then for Bronsted and Lowry concept, there are two scientists who bring up a concept of acid and base. The acid was defined by Bronsted and Lowry concept as proton donors. Proton donors. Whereas bases is defined as proton what? Acceptors. Yes, acids are defined as proton donors, whereas bases are defined as proton what? Acceptor. Let's see example. One of the notable acids we have is ACl. We talked about it before now. We said that ACl is a proton donor. Oh yeah, let's see. When you dissolve ACl in water, what do you have? You now see that hydrogen here, which is a proton, will go to water and attach to produce hydrozonium ion. Then this Cl minus will come out. Yes, this Cl minus will come out, then hydrogen will attach to this to give you this. That means acids are proton donors. This HCl donated hydrogen ion to water to give you hydrozonium ion. This simply means hydrozonium ion. Hydrozonium ion. Okay? So because this donated proton, which is hydrogen, to this, to give you this, we call this an acid. Now for bases, they are proton acceptors. Okay? This is a typical example of what? A base. When this base reacts with water, hydrogen from water will go to this ammonia, and that means the ammonia will be turned to ammonium ion plus what? OH ion. That means this is a base, whereas this is a what? Acid. Okay? I hope you get what we are saying. That because this is able to donate proton to this, we call it proton donor. It's giving you this. And that will also suit what Arrhenius concept talk about. Because Arrhenius, when you are talking about water, is donating hydrogen to get hydrozonium ion, or which we can also say hydrogen ion. Yes, bases when dissolved in water is getting like ammonia when dissolved in water is getting ammonium ion and OH ion. Okay, and so it still go in line with what Arrhenius said when we are talking about water aspect. So this donates proton to water, while this accepts proton from what? Water. Okay, then we go to Lewis concept. From the point of Lewis, Lewis says that an acid is a substance that is capable of accepting electron, a pair of electron. So acceptor of what? pair of electron. Y base is or are substances that have the tendency to what? Donate a pair of what? Electron. How do we mean? Let's go to Lewis structure of some substances. Let's go to ammonia. Look at the molecular formula of ammonia. Ammonia has how many electrons? Nitrogen has 7 electrons, right? Nitrogen has 7 electrons. Nitrogen has 7 electrons. That means the inner shell will have 2 electrons, while the outermost shell will have what? 5 what? Electrons. Now, the outermost electron is what we need to draw the Lewis structure of what? Ammonia. We write 5. We have 5 for nitrogen. For hydrogen, hydrogen has how many electrons at the outermost shell? 1. And there are 3 hydrogen. 3 times 1, 3. Plus 3. That will be giving you a total of 8 electrons. Now, how do we draw the structure? One thing you do is you write nitrogen, yes, then surrounded by what? 3 hydrogen. Yes, nitrogen surrounded by what? 3 hydrogen. Then assign pair of electron in between the bonded atom. I can use this symbol to do the assigning, or use this symbol. So let me use any. I have assigned 6, but what we have is 8 electrons. That means it's remaining what? 2. I will keep that 2 on the nitrogen part. Why? Hydrogen have been able to attain its duplet structure. Hydrogen duplet structure, but nitrogen is meant to attain octet structure. And so, if this 2 is given to this hydrogen, this hydrogen, that will be wrong, because the nitrogen will end up not having 8 electrons. That is octet structure. And so we say this is the structure of, or Lewis structure of ammonia. That means in Lewis structure of ammonia, it has a lone pair of electron. That is 2 electrons that is not bonded to another element, or yes, that is not bonded to another atom. Okay, it has 2 electrons, or what we call a lone pair of electron. A lone pair of electron means 2 electrons, which is not shared by any atom. It's only under nitrogen, as you can see here. Now, because this nitrogen or this ammonia has a pair of electrons which is to be donated to form a coordinate bond with another molecule, we say that it has a pair of electrons for donation. This is what we call Lewis base. Lewis base, because it has a pair of electrons which it can donate to another molecule to form a coordinate bond. Oh yeah, let's see what we mean. Now, there is a compound called BF3, that is trifluoroborane. That means when you have this B represent boron. This boron have 5 electrons, and because it has 5 electrons, the implication is that the inner shell will have 2, the outermost shell will have what? 3. So the outermost shell has 3, the way nitrogen also have their own. Nitrogen, the inner is what? 2, the outermost shell is 5. So 2 will be here, then 3 will be shared by what? Hydrogen. 1 from nitrogen, 1 from nitrogen, 1 from nitrogen. then the hydrogen is the one supplying the second electron, second electron, second electron. Now what we have here is that we have three electrons from what? Boron. Now fluorine needed 1 electron. This is for fluorine. Fluorine is 2 here, inner shell, and 7 at the outermost shell. Because fluorine has 9 electrons, right? 9 electrons. Now, the implication of this is that fluorine needed 1 electron to attain what? Outer structure. Fluorine needed 1 electron to attain what? Outer structure. So, total outermost shell of fluorine is 7. 7 times 3. We are dealing with the outermost shell. We are not using the full electron. So, for boron have 3 at the outermost, plus fluorine has 7 at the outermost. 7 times 3, 21. That will be giving you 24. Right? Boron, surround it with what? Fluorine. Okay? The implication is that rule number 1 of Lewis structure is assign pair of electron to in between the bonded what? Atom. Assign pair of electron in between the bonded what? Atom. We assign 2 here, 2 here, 2 here. That gives us what? 6. 24 minus 6 will give us 18. So I will assign 6 here to make fluorine octet. Assign 6 here to make fluorine octet. Assign 6 here to make fluorine octet. This fluorine is 8, this fluorine is 8, this fluorine is 8. 8 plus 8 plus 8 will give you the total number of 24. That means you are done with the assigning. Now you notice from this structure that the boron has 6 electrons at the outermost shell. 2, 2, 2, 2, 2, 2. That is 6. That is, its outermost electron is not up to 8. And it's meant to have outer structure for it to say that it has met up the outer structure we want. And so because it does not have because it does not have up to 8 electron here, what will happen is that this ammonia will be sharing this lone pair it has with the boron. That is making ammonia to still be 2, a total of 8, and this one will still be 2. See what we mean? You say N, where that lone pair, this lone pair is here now. Then this one plus F where the lone pair will be here. Okay? Then remember that we have the remaining 6 here. Remember that we have the remaining 6 for fluorine here. Okay? Now, these 2 electrons will now be shared by what? Nitrogen and what? Boron. And once they are sharing it, look at the arrow. The arrow will point this way. Nitrogen sharing its lone pair of electron to boron. Boron. This lone pair of electron is what form this bond, this hydrogen bond. A pair of electron form hydrogen bond, so you have it this way. Then fluorine. So the direction of the arrow tells you which of the molecule is donating the what? The lone pair of electron. That molecule donating the lone pair of electron is called Lewis base. Now the molecule which accept the lone pair of electron so that they will be sharing it. So they are sharing this lone pair of electron. That lone pair of electron which form this bond, the arrow bond. The lone pair of electron is shared by nitrogen and what? Boron. So this boron which is enjoying this lone pair of electron with nitrogen, making boron to be 2, 2, 2, 2, 8. Nitrogen 2, 2, 2, 2, still 8. Making it to attain its hottest structure. That trifluoroborane will be called Lewis acid, because it is accepting pair of electron from a Lewis base, whereas the one donating is called Lewis base. So you need to know this as we go into this topic in full. That is for this and this is for this. This is an example of Lewis acid, whereas this is an example of Lewis base. This came up as a result of Lewis structure. The information we got from the Lewis structure, and as I said, the Lewis structure make use of the outermost electron. The Lewis structure make use of the outermost what? Electron. So it is the outermost electron, like this one, outermost electron is 3. Outermost electron of fluorine is 7. 7 times 3, 21. You add it up, 24. That is what we will be assigning. Assigning a pair of electron in between the bonded atom. Then the remaining electron assign 2, 2, 2, 2, 2 to make this one hottest structure. Assign 2, 2 to make this one hottest structure. It remains 6. Assign it here to make this one hottest structure. Electron has finished. Making this plus this plus this to be 24. And since it is 24, it means that there is no electron we can put here to make boron 8. And so boron is lacking extra 2 electrons so that it will get to hottest structure. And so it needs to get bonded with a Lewis base which have excesses of a pair of electrons so that it can attain to hottest what? Structure. And so we call trifluoroborane Lewis acid and ammonia Lewis base. Next we want to look into is important formulas we needed to know while trying to calculate pH of a solution, or acidic solution or basic solution. Okay, let's see. For us to do that, we need to recall to ourselves those information we just said before now. That is, that an acid, this is an acid because it has hydrogen ion, in which when it reacts with water, this hydrogen ion will come out. Or this is an acid that has hydrogen ion to be donated to water, because we said from a field of Bronsted and Lowry concept, an acid is a substance which has the tendency to donate a proton or hydrogen ion to another species, and so it has hydrogen ion to be donated to water. So we call this an acid. And so since this is an acid, we now say that when it reacts with water, it will be giving you hydrozonium ion. That is, it's donated hydrozonium ion to this, okay, to this water, and it will be forming a what? A conjugate base. A conjugate base is a base gotten after hydrogen ion has been removed. A conjugate base is a base gotten after hydrogen ion is removed. So here, hydrogen ion has been removed from it. So there is deprotonation. There is what? Deprotonation. That is, hydrogen ion has been removed from A. So we call it conjugate base. Now, remember, we are considering weak acid. That is the type of acid we are looking into. Yes, how to get the pH of a weak acid. The reason is because when this acid, which is weak acid, is to be considered, we said, or when we considered it before now, we said weak acid has unionized and ionized part. When it reacts in water, it will get the ionized part. Now we say let the fraction of the ionized part be A. Let the fraction of the ionized part be A. Now, fraction of the ionized part plus fraction of the unionized part will give you 1, because total fraction is 1. That means fraction of the unionized, which is X, is equal to 1 minus fraction of the ionized. We are using A to represent fraction that ionized. And so that means that fraction that are unionized is 1 minus A. Where do we get the unionized part? This is unionized fraction. Unionized fraction part. So the unionized part will be inside here. The unionized part will be inside here. And so we say that here is 1 minus what? A. That is the fraction of the unionized part. That means when a weak acid is dissolved in water, the ionized part is A. The unionized part is 1 minus A. Now, if you are looking for the concentration of the ionized and unionized part, what you do is that if the total concentration is A, total conc is, let's say, C. Total conc equals to C. The implication is that for me to get the total concentration of this hydrozonium ion which ionized, I'll multiply it by C. This one, I'll multiply it by C. Okay? Then for me to get the total concentration of the part that is unionized, I'll multiply this one by C. Now, this is water, is neutral. Okay? Now, we now go to get the ionization constant of the acid, Ka. Ionization constant of the acid using Le Chatterley's principle means concentration of the what times what? Concentration of this, that is their product part, all over concentration of what? The reactant part. And that means, what do we have as this? AC times AC all over 1 minus AC. Yes, that is the value for Ka. Now, it is important to note that whenever you are talking about weak acid, the ionized part is too small or is tending to infinitesimal, tending to 0. The ionized part is more of tending to 0 because it will have more of unionized part. When you are talking about weak acid has more of unionized part than ionized parts. That is why we are making use of it, or we are trying to produce our products to ensure that it is weakly acidic, because it will have more of unionized part which the body will make use of. And so the ionized part is tending to 0. It's more of infinitesimal. Is more of insignificant. And so we say this ionized part will be taken to be what? 0. This ionized part will be taken to 0 because it will have more of unionized part. And so when it tends to 0, 1 minus this will be 1. That is more of unionized part. This C will cancel C. 1 minus this is 1. That will be giving you that A times A square C is equals to what? Ka. We have gotten the final value for Ka. We now say that we make our A square subject of formula. It will be giving us Ka all over C. And we also say that our A is equal to square root of what? Ka all over C. That is the formula for this ionized part. Now, look at this hydrozonium ion is AC. We now say that the concentration of the hydrozonium ion is equals to AC and is equals to A is what? Square root of what? Ka over C times C. Please don't make a mistake and start bringing this C inside here. This C is not inside square root. And so, for you to be able to simplify this, remember that C is same thing as square root of what? C squared. Yes, from knowledge of mass. Power of 2 will cancel square root. And so we will tell them that this means square root of what? Ka over C times square root of C squared. Then what we'll be having is that hydrozonium ion is equals to square root of Ka all over C times C squared. This will cancel this, C will remain. Therefore, hydrozonium ion concentration is equals to square root of KaC. So, we have noted this now. Remember, in this ionization constant formulas, we said that this closed bracket denotes concentration. Okay? We are talking about concentrations. Now, from here, it is noted that negative log of H3O plus is equals to pH. We call it pH. P means negative log. Then H3O plus is talking about hydrogen ion, so to speak. And so what we will do now is we now say that we will take negative log of both sides. We will now have minus log H3O is equals to what? Minus log KaC all raised to the power of half. Okay? Now, because this half means square root, that is why we package it this way. This means that this means pH of the acid equals to minus, that 1 over 2 will come this side, minus 1 over 2 log, then KaC. Now, what we will now do is that we tell them that this means pH equals to, I will open the bracket, I will say minus 1 over 2 log Ka, then minus 1 over 2 log C. Okay? Now, minus log, note that minus log Ka is called pKa because P means minus log, and so minus log will be pKa. We call it 1 over 2. Minus log is P, then Ka, then this one is minus half log what? C. That is the formula we will use to get pH of acid. Watch this formula and note it very well. Okay? Yes. That means if they ask you to get pH of an acid, tell them it's 1 over 2 pKa minus half log C, where P means minus log. Okay, we want to see how to solve this problem on pH of acid. Okay, question number 1. For the given sample of 0.01 mole per dm cube of benzoic acid, calculate its pH given that Ka is this. Now, noted is an acid. So to get the pH, we said using the formula pH equals to 1 over 2 pKa minus 1/2 log C, where C is a concentration. Now, the concentration is given to us in mole per dm cube, that is 0.01. So what we will tell them is that pKa means, that P means minus log. So 1/2 times minus log, what is our Ka? 6.5 times 10 raised to power minus 5. Then minus 0.5 log what? 0.01. That is the what? Concentration. Okay? So you are getting 1/2 minus log is gotten from P means minus log. Then Ka is this. So what you'll be having here is that 0.5 log 0.01. That will be giving you minus 1. Then 1/2 times, then there is minus 0.5 log 0.01 will give you minus 1. Then 1/2 times minus log 6.5 times 10 raised to power minus 5. If you check up this, it will give you 2.09. That is 2.09. Minus times minus will give you what? Plus. That will be giving you 2.09 plus 1. And finally, the answer should be 3.09, approximately 3.10. So the pH of the benzoic acid is 3.10. Please try to confirm this with your calculator and use the comment box below to tell me yes, it is correct. So if there is any aspect of it that is not correct, you will check it up. 0.5 is half times this, it will give you 2.09. Then 0.5 log 0.1 will give you minus 1. Then minus times minus plus, it gives you this. Go to question number 2. Calculate the pH of a 50 mg per ml solution of ascorbic acid with molecular weight 176.1 pKa. This is important for you to note that molarity of a substance is a mole per what? Mole per dm cube or mole per liter. That is about molarity. Then concentration of a substance, mass concentration, mass conc is equal to milligram per ml, which is equivalent to gram per what? Liter. Please, milligram per ml and gram per liter are the same. Yes, milligram, milligram, milliliter. If m cancel m, it gives you gram per liter. Are you getting it? So, having it in mind, this is milligram per ml. I supposed to convert it to gram per liter, but because it is milligram per ml, I will say this is equivalent to gram per meter. And so, what I will tell them is that concentration, which is mass conc over molar mass, the mass conc is 50 milligram per ml, which is gram per liter. Then molar mass is 176.1. With this, we get the molarity. Okay? After getting the molarity, we now look at our pKa. We now go to this formula. Tell them that your pH is equals to half pKa, 1/2 bracket 4.17 minus 1/2 log. This 1/2 means 0.5 log. What is the concentration? Log 50 all over 176.1. So you use your calculator to compute it. So after computing this and this, it will be giving you 2.36. So I want you to use your calculator and confirm it. Also comment on the comment box below. Tell me yes is correct or no, then correct me. Thanks for watching the video.